Welcome to the river module. We'll start off with a little bit of terminology. When we're talking about river systems, the, some of the root of some of the words has fluvial in it. You'll see FLUV, and that's just simply calling that it's stream related. So don't stress about that. But if you see fluve in a word, you'll know that it's related to streams. And also, this is when we start doing the transportation of material. So that's erosion. Erosion is the moving of material. And so one of the things that rivers are really good at is transporting sediment and some sand and gravel, depending on how much of a force it has behind it. So this is erosion by streams, is the transportation of that material by streams. Now, streams will drain what's referred to as a drainage basin. So the idea is that what direction does water flow? Downhill. So in any given area, if you've got mountains or hills, there's going to be a highest point. And water falling on one side of that highest point is going to flow off in one direction, and water falling on the other side of that highest point is going to flow in a different direction. So when you see this kind of slight hill here, this is that dividing line between where water would flow in this direction and where it would flow in this direction. That's referred to as the drainage divide. It's the division between two drainage areas. And so the area between the streams is referred to as an interfluve. Hey, look, it's fluve. It already showed up again. So it's between the streams. So it's kind of recognizing that a drainage basin and stream activity isn't just where the river is. It kind of covers a much larger area. So locally in Orange County, our mountains just inland from us are the drainage divide between drainage that goes into Riverside County and drainage that goes into Orange County. You can look at drainage basins based on individual streams. And so in this picture here, these are small streams covering a small area. So for this particular stream right here, this is its drainage basin. For larger streams, such as the Mississippi River, well, all these other smaller streams kind of feed into it, and so the Mississippi River's drainage basin is significantly larger. But it's made up of other rivers that feed into it. So the Missouri River drainage basin also includes the Platte River basin, which also includes the Little North Platte basin, which also includes the Laramie River. So you can see where I'm getting here. And it's always shocking to people to see that how much of the United States the Mississippi River drains, and including parts of Canada as well, and how close it is to Lake Michigan up in here. And so things like the Erie Canal would connect drainage basins, and then the Chicago River actually allows for shipping between the Lake Michigan and the Mississippi River basin. So the Continental Divide would be the large-scale drainage divide between the western United States and the eastern United States. So rain that falls over here drains you into either the Gulf of Mexico, the Pacific Ocean, or it drains into, like, there's interior drainage here in what's referred to as the Great Basin. Everything over here is Gulf of Mexico, Atlantic Ocean, Hudson Bay, that kind of thing for drainage divides. So Saddleback College sits on an interfluve because we're between the drainage for the stream that kind of parallels along the 5 freeway. Oso Creek is the one that runs kind of through here parallel to the 5, and then San Juan Creek comes in, and then they merge in San Juan Capistrano. So the drainage basin for Oso Creek would be this area, and then San Juan would be in this area, and so Saddleback College is in that kind of hill between the two drainage areas. Here we can see a little bit bigger picture of the drainage basins in Orange County, and it's always fun to, like, what drainage basin do I live in? So the big scale, the Continental Divide, there's always signs along the side of the road that Atlantic Ocean drainage, Pacific Ocean drainage. So when we take pictures when we were kids, and I'm the one in the middle, that's my mom, that's my brother, we would always stop and get corny pictures at the Continental Divide. I still have them as an adult, by the way. And when we were at Loveland Pass, this is, if you've ever driven I-70 through Colorado that goes through the Rocky Mountains, at this point the Eisenhower Tunnel goes through the Rockies and avoids this narrow winding road up and over to a 12,000 foot elevation, where you could see how that'd be dangerous and kind of would restrict traffic during the winter. But of course we wanted to go up there. So I could go up there and along the drainage divide, the Continental Divide, pour water here, and that would flow off into the Pacific Ocean, and pour water here, that would flow off into the Atlantic Ocean. Looking at all of North America, you can see the multiple drainage basins that we have. California, I always think they got lazy when they did this one, because they went, well, let's just make it all of California. There's a whole bunch of smaller ones. You saw the map of Orange County a few seconds ago. There's a whole bunch of smaller drainage basins, and so they kind of, rather than map all of those smaller ones, they created like one big and said California, and they're just lazy. Now the streams, as they cut into the rock and remove material, they're going to be influenced by what the structure of the rock is itself. Now we already talked about folding and faulting, and that's going to create cracks or patterns in the ground and in the underlying structure. And some rock may be weaker than other rock, so it will affect how it happens. So if we look at an area where the rock is uniform, it's not cracked, where it's pretty consistent, you're going to create this dendritic pattern. This is a pattern we see like on the backs of leaves. It's a system that kind of nature evolves to kind of equally drain areas, and it creates this what looks like branches on a tree. This would be the one that would tell you there's nothing weird in the underlying structure. All the other ones, something else is going on. Trellis, for example. Trellis and parallel, these both could be a series of folds. And so as the erosion cuts through, it's going to be influenced by those different rocks in kind of a linear pattern. And that would create either this parallel pattern, depending on what direction it was, or this trellis pattern. Radial, what direction does water flow? This one always makes me laugh, because people are like, it flows downhill. So if all of these streams are flowing away from this center portion, what is this? It's some kind of hill. Well, if it's a nice roundish pattern like this, where it's all coming off in all equal directions, this is typical what you would find in a volcano, would be a radial pattern radiating away from it. But it's not exclusive to volcanoes. Anytime you got a single peak or a hill, you could get that. Rectangular is typically from fractures in the rock, where you get large scale jointing. And then annular, this one's weird. I'm just going to tell you about it. I'm never going to test you on annular. Things that push up from below, maybe it's some... Typically it's salt. You find these in the southeastern United States and Louisiana. And so salt kind of gets squeezed together in the underlying sedimentary layers. It's semi-fluid, and it'll push upward through the layers of sedimentary rock in like a single round blob coming up. It's almost like a plug of molten magma coming up, except it's just a big plug of salt. So it bends the rock upward in a circular pattern. So it cracks the rock in a circular pattern. And so one of the things that people look for when they were going to do salt mines is in the South is they would look for this circular drainage pattern, and that would tell them that there might be salt below. It also works for, in some cases, this isn't like universal for everybody looking for oil, but for areas that have consistent layers of sedimentary rock, it also works for areas where there's some petroleum beneath the surface kind of pushing up. And so they would also look for this pattern for where they would do it. Whoop, sorry, I went too fast. My mouse, I'm using a new mouse and it's super sensitive. Probably the only two I would test you on the exam, hint, hint, nudge, nudge, would be the dendritic pattern, which is showing that everything's kind of consistent under the surface, or the trellis pattern, because that's the one that's influenced by what we would see on the east coast of the United States because of the folding that we find in the Appalachians. Here you can see the nice, beautiful trellis pattern. This is pretty common to what we have around here. This is the deranged pattern, which I'm not even going to cover. So in Australia, the Katherine River is a really bizarre river, and you can take boat rides up it, but it's as you're going up this river, it makes these literal 90-degree turns. And so the streams out in the western United States, they've got that kind of, smooth curving pattern, or even if you're in the Midwest, those have even more curvature to them. Nope, this is right angles. Well, this is large scale fracturing of the rock that is over hundreds of meters or tens of meters, and so those fractures in the rock are at right angles, so that's where the weakest point is, and so that's where the stream flows through. Well, when we talk about streams and their ability to transport and remove material, that is its discharge. So the higher the discharge, the more it can transport. So if it's got a low discharge, it's not going to be transporting much because there's just no energy behind it. High discharge, it's going to be able to transport more. So I'll go more into this in just a second. And by the way, there will be no math on the test. But discharge is a function of three things. It's affected by how wide is the stream, how deep is the stream, and how fast the stream is going. So if any one of those increases or decreases, it affects the discharge. Typically, velocity is the big one, so the faster the stream is going, the more it's going to affect it. But for the simplistic purposes here, we're just going to talk about that all three of these, if any of them change. So we'll see some streams that are really, really, really wide, but they're not that deep and they're not that fast. So even though they're wide, the low depth and the low velocity means that they're not really having a high discharge. Then we'll have some that aren't really that wide, but have a really high velocity, and so they'll be able to transport materials better. So the higher the discharge, the more erosion and transportation takes place. The lower the discharge, the lower the erosion and the lower the transportation that takes place. And it's going to affect what it can transport, not just how much, it's what can be transported. So the what is the stream load. This is what the stream is transporting. So the material that falls into solution into the water, that's referred to as the dissolved load. So minerals, salts, some really, really, really fine-grained clays would be part of the solution load. The suspended load would be clay, fine-grained stuff, but bigger than grains of sand. So this is often what gives the river its color. That and the solution load are often what gives a river its color, whether it's green, whether it's brown, is part of the suspended load. So as the discharge increases, the bigger the pieces you can move. So the smaller the discharge, you're only moving the solution load. A little bit of a current, you can move some of the fine-grained clays. Once you get faster, you can start pushing sand along the bottom. That's the bed load. Sand tends to kind of bounce across the surface. Sometimes it rolls, sometimes it bounces, but it's the material on the bottom of the stream that's moving is the bed load. If the discharge is high enough, you're going to start to see some rocks move as well. And all of that is part of the stream load. So the higher the discharge, the more stuff you're moving in the bed load, and the lower the discharge, you're only moving either the suspended load or the solution load. So the suspended load, that's the clays. So we can see here from the Mississippi River, all of that fine-grained material creating the Mississippi River Delta and slowly falling out of suspension into the Gulf of Mexico or Gulf of America, depending on when you listen to this particular video. And then the Colorado River, this particular part, it's not a high velocity like it is in other parts, but it's still moving a lot of clay and a lot of fine-grained material through in the suspended load. You can, if you ever go into the Colorado River, down at the bottom of the Grand Canyon or some of those areas, it's like mud almost in some places. Now, to give you an idea how much suspended load is in the Mississippi River, this is just outside of New Orleans, and this is after Katrina in the 2000s, and so the Mississippi River overflowed its banks, and so once it got into this area, it wasn't flowing anymore. So what's the velocity? 0. So can it move any of its load anymore? No. So all the load that flowed into this area, since it's not moving, the velocity is 0, what happens to all the stuff it was carrying? It just kind of settles in place. So for a long time after Hurricane Katrina, they were spending time just getting rid of all that mud and clay that came in that suspended load when the water overflowed the levees and into New Orleans. Bed load, the gravel. Now these two pictures, you could only see the bed load when there's not stream flowing through it for the most part, simply because if the bed load was moving, it would be underwater and you can't see it. So these would be streams that have varying flow rates. I actually don't recall where this one was taken, but this is local in Orange County. Here we have Trabuco Creek. This is out by Robinson Ranch, O'Neill Regional Park, and this is during the dry season, which for us would be spring and summer and fall. So the water flow, the discharge is significantly lower. But what's transporting and moving all this material would be during the wet season. So all of the stuff that's transported by the stream is referred to as alluvium. And so alluvium is that fine grain, rocks, gravel, big stuff. So anything that's been transported by the stream is referred to as alluvium. Now I'm pointing to the stuff here in the stream bed itself, but notice all this material on the side of the hill. This would have been from centuries ago, or sorry, thousands of years ago, when we had a much higher discharge rate in this area, much more rainfall. So the stream was able to move more material than it can now. And so we see all of this stream deposited material that's also referred to as alluvium. So when we talk about desert landforms, we'll talk more about alluvium there as well, but that's stream deposited material. It's not typically well consolidated. It's not solidified into a rock. If it did, it'd be conglomerate, but this is just stream deposited material. Here you can see more alluvium here and some previous flows up here that deposited all of this fine grained stuff too. So that's a student in the class, and he thought he had a cool shot of the alluvium at Trabuco Creek. So here, this is a photo from my hotel room. This Aguascalientes is at the base of Machu Picchu. So if you go visit Machu Picchu, you have to go through Aguascalientes. And we're noticing this nice stream running behind our hotel room, but it was really noticeable that it was scoured up the side. And what the hell would have moved these big boulders? Well, they have a wet season and dry season there, but they get tropical rains, which are far more extensive, so they're much larger. So their wet season looks like this. So that has a significantly higher discharge, and that's what's able to move these boulders, is this kind of discharge. This was from a fellow geographer who was there during the wet season. We were talking about I was talking about how peaceful Aguascalientes was, and he's like, we couldn't sleep at night because the river was so loud. And now I know why. This is his picture. All right, I'll come back with more stream stuff in what I'm going to call part 1.5, because I'm recording this part 1 into 2 pieces. So we'll talk about intermittent streams and other stuff when I come back with part 1.5.